Yep. Okay.
So good evening, everybody. Welcome to the Hanbury Endowed Lecture in Historic Preservation. My name's Andrew Johnston. I'm the director of the program in Historic Preservation here at UVA. This evening, I have the great pleasure to introduce Dr. Patrick Malone, an Emeritus Professor of American Studies and former Director of Urban Studies at Brown University. Patrick Malone is an industrial archaeologist and a historian of technology. He's former president of the Society for Industrial Archaeology, and for 15 years was the director of the Slater Mill, a historic mill complex on the banks of the Blackstone River in Rhode Island. His primary research interests are the urban built environment and industrial development. He's also done a great deal of work in public humanities, focusing on museum interpretation, park development, historic preservation, and the recording of engineering structures. Much of his scholarship examines American rivers and hydraulic engineering. He's the author of Waterpower in Lowell from Johns Hopkins University Press, 2009, which was the winner of the 2010 Neverson Award from the Association for Industrial Archaeology, and co-author of The Texture of Industry, which I have here, an archaeological view of the industrialization of North America. This book's from Oxford University Press. This book won selected as Outstanding Academic Books by Choice Current Reviews for Academic Libraries, and was a recipient from the American Institute of Architects International Book Award. His present research focuses on a unique tidal water power system in 19th century Boston. And his talk tonight, Dams Beneath the Streets, the Industrial Heritage of Boston's Back Bay. Please join me in welcoming Professor Patrick Malone.
Industrial heritage is not always easy to preserve or interpret. There are painful memories of environmental damage, dark satanic mills, and exploited workers. Negative views may overwhelm lingering pride in craft skills or technological achievement. However, public perceptions can change, as they have in Lowell, Massachusetts, where residents have developed a growing interest in the history of the textile industry that made their city famous and then abandoned it. It has helped that a National Historical Park now draws many thousands of visitors to Lowell, and that almost every factory has been adaptively reused and its handsome architectural details rehabilitated. You can't forget the presence of industrial heritage in a city filled with mill complexes, tall chimneys, and power canals. The Boston Associates, who founded Lowell in the 1820s, left indelible marks on its urban landscape. Many of those elite Bostonians were deeply involved in an earlier scheme to create a vast industrial complex at the western edge of their own community. Over time, that effort radically transformed the shape of the city, but none of its features are visible on the surface. The industrial heritage of Boston's prestigious Back Bay district is hidden, misunderstood, and largely forgotten. Jefferson's embargo in the War of 1812 had devastated the maritime economy of Boston. In desperation, merchants were turning, in Samuel Eliot Morrison's words, from the wharf to the waterfall. Francis Cabot Lowell was testing his power loom for a new factory on the Charles River in Waltham. There were no waterfalls in Boston, but the seaport did have a substantial tidal range of 10 feet and experience with traditional tide mills. Some highly creative men in 1813 came up with a new way to harness the tides and an ambitious plan for powering industry in the Back Bay. Lowell was soon backing his friend and occasional business partner, Uriah Cotting, the leading promoter of the Boston and Roxbury Mill Corporation. Cotting proposed a corporation that would build and operate a perpetual power system. That system of dams, sluices, basins, roads, dikes, raceways, and mills was designed to supply continuous, uniform tidal power, 24 hours a day, every day. I've just finished an article about the system with Bob Gordon from Yale University. It's in production at the journal Water History. We're working on a much longer book together. Round-the-clock manufacturing was a sharp departure from the practice of all previous tide mills, which were intermittent in operation, conforming to the 12.4-hour tidal cycle. Starting times changed with each cycle, making regular work schedules impossible. Most millers captured water at high tide in a pond and released that elevated water to power their wheels only when low tide was approaching, and then they could operate for only 3 to 6 hours. Providing tidal power continuously for industrial enterprises was unique. Instead of a single mill pond, there would be 2 basins. Industries would draw water from one basin that filled at high tide, pass it through breast wheels for mechanical power, and discharge the tailwater to another basin that emptied at low tide. Automatic sluice gates would maintain proper levels in both the full and the empty basin without the need for human operators. A series of schematic diagrams later in this talk will show you how it worked. This German map of Boston and its military resources in 1776 reveals the geography of the city. Boston is really a peninsula connected to the mainland by a very narrow neck the Charles River comes down and creates a large estuary. And this is the area which we know as the Back Bay, and that'll be the focus of most of this talk. Many prominent Bostonians saw the need for industrial development with mechanical power. The former Tide Mill Cove, which is right up here, had actually ended operation in the early 19th century, and they were filling that area. Steam engines were still unreliable, and fuel for boilers was expensive. Recovery of artifacts from the mid-18th century South Mills at the bottom of the Mill Cove was part of the Big Dig project for a new highway through Boston. Unfortunately, the survey for potential archaeological sites missed the South Mills, and the recovery of a few artifacts was done by construction crews without proper controls or recording. Nevertheless, historical research and analysis by the University of Massachusetts, Boston has been very fruitful, and an impressive book may eventually result. In the meantime, one of the millstones has been put on unexplained display near the mill site. No sign on it whatsoever, and as you can see, they don't shovel it well. As part of the research team for this project, I hope the signage will eventually describe its significance. Now, here are the dams that Cotting started in 1818, but his original 1813 plan was a little different. So let me first explain what he said he would do. He planned to create basins by putting a dam from essentially the Boston Common over to Gravelly Point in Roxbury. It was going to be here south of the dam he actually built. And that would be the full basin. And it would draw its water from the Charles River estuary at high tide, and it would stay largely full. He was going to also build a dam here by the South Boston Bridge. And this South Bay was going to be the receiving or empty basin. Boston selectmen gave overwhelming approval for the design. Not too surprising, since Charles Bulfinch ran the committee and he worked for Cotting on a number of development projects. But Boston stood to benefit. The problem was that the citizens of Roxbury were horrified by the idea of what they called a dry dock in the South Bay. And they had a Roxbury Canal here, and they had some wharves, and they didn't like the idea of an empty basin that would cut off their waterfront. It was really going to completely disconnect them from the sea. The plan changed as an act of incorporation for the Boston and Roxbury Mill Corporation moved through the legislature in 1814. The main dam was extended for a distance altogether of 1.5 miles, and it would run all the way to Sewell's Point in Brookline. They also came up with a cross dam here, which would separate a full basin, would separate a full basin from an empty basin. What really changed dramatically was that Roxbury had enough influence in the state legislature that instead of having a nice full basin of water next to the Boston Common, this became the empty basin. And the full basin would be over here. Roxbury was pleased because they weren't going to be cut off from the sea, but Boston was going to end up with something that might smell, certainly at low tide. The location here, for those of you who are familiar with Boston, is really just about where Kenmore Square is. And this dam follows the line of Beacon Street, which runs just below Beacon Hill. This map of Boston and its immediate surroundings in about 1821 has key features identified. It shows the tidal power system as completed. New dams are red here, and new toll roads are green. And these are some new toll roads. But the mill dam itself is also a toll road. And that was one of the things that Boston really liked about this plan, because it gave them a new connection to the mainland. Bridges are shown in yellow, canals are bright blue, the full basin is tinted dark blue, and the receiving basin, spelled in a rather unusual manner on this map, is here in a lighter blue. The base of this is the John Hale's 1819 map. And I used Photoshop to simulate the layering capabilities of a geographic information system, which we did use to determine areas and distances on georeference maps. The historic maps in this show were courtesy of the Leventhal Map Collection at the Boston Public Library. The highest tides impacted not just the full basin itself, but they spread out over salt hay marshes that were valuable property. And they also represented potential power that could not be built. The leases for power were for a perpetual minimum, not for an occasional maximum. The number of mills on this 1821 map by Hales represents an ambitious projection. Cotting hoped for even more, estimating 81 mill powers, each equivalent to the power needed for one set of gristmill stones, or about 10.3 gross horsepower. He was overly optimistic and had done no engineering analysis at all, as far as I can see. Cotting envisioned a diverse selection of manufacturers, all with long-term leases for power. In total, the Boston Roxbury Mill Corporation leased only 16 mill powers, even though he'd hoped for 81. And all of that was between 1822 and 1832, when the Boston Waterpower Company was formed to manage the system. And there were just 6 tidal-powered sites that were developed. The mills that are shown here are being fed by the full basin through races that you cannot see, and then they would empty into this tail race that would go into the receiving basin. The sluice gates are out here and actually shown. This is the sluice gates that open to fill the full basin, and these are the gates that open to allow water to empty from the receiving basin. I'm going to use a set of schematic drawings that I worked on with historical architect Chuck Parrott to show this perpetual power system in operation through one tidal cycle. The elements of the system are a body of tidal water outside the mill dam, and I show that at 2 different points here. This really sections through the mill dam, both at the full basin and at the empty basin. B represents the full basin, a body of water that fills at high tide and supplies power to the mills continuously. There's a larger receiving basin, and that has to store water discharged from the mills until low tide, and then it can empty again. Sluices in the mill dam open automatically, open or close automatically. I'm going to just step back once so you can see once again where we're talking about. So the full basin, the larger receiving basin, the sluice gates in the main dam. And then the mills would be positioned either on the cross dam or on Gravelly Point. And they would draw their water from the full basin and discharge it into the receiving basin. Now, this is the situation at high tide. The high tide has opened the gates to the full basin, and water is flowing in. At the bottom here, we have a plan view so that you can see the operation of the sluice gate. So the water is flowing in to the full basin. Gates to the receiving basin are closed, holding out the high water. Mills will draw water from the full basin and discharge it into the receiving basin throughout the tidal cycle, and this is continuous power. Next, we have ebbing tide. All the gates are closed, isolating the full and the receiving basin from tide water. And then next, low tide. And at low tide, the gates at the receiving basin automatically open because the water level has risen higher than the low tide. So it pushes them open and water discharges or empties. The last schematic is of the flooding tide as the tide comes back into the Charles River Basin. Again, the gates are closed, and once the water gets high enough to open these gates, it will replenish the supply in the full basin. This map is from Nancy Seischel's book, Walking Tours of Boston's Made Land. She's the authority on making land in Boston. Wrote another book called Gaining Ground that's really a fine study. But this is an example of a tour program that she operates. And the map is somewhat confusing, so I'm not going to try to explain it to you. But I want you to see how you actually can overlay an original shoreline onto a current plan of the city, a map showing the streets and Back Bay Fens. The gravelly point, which is the center of this entire project and where most of the mills are located, is here. And this is the cross dam. And the cross dam, you'll notice, runs right by Commonwealth Avenue and Mass Avenue. And we'll see that location later. The important thing here is that Beacon Street is the main dam. Now, her guided tour makes mention of the Back Bay Power Project, but that's not really the focus of her tour, though she probably will continue to develop new ones. Chuck Parrott based this section drawing on a description from engineer E.H. Howe in 1880. Howe had removed some of the dam while building the Fen Park for Frederick Law Olmsted. The large stones, the ones here in the main walls, were Roxbury conglomerate, known locally as pudding stone. There are numerous mentions in the corporation records of specific ledges leased at Parker Hill and Roxbury. The drawing also shows smaller ballast stones, which are piled against the interior of the wall for support, mud retention, and drainage. Howe did not mention finding any of the external buttresses, and they actually did put some exterior buttresses if the walls were starting to swell out, which they did in a few places. We know that Irish contractors got most of the work packing mud into the dam. Laborers were apparently recruited in Ireland specifically for this large project. Pudding stone formed the walls of the main dam and the foundation of the first mill on the system, a grist mill powered by 2 breast wheels. It later became a popular stone for major buildings, including many Boston area churches. I marked this 1832 map of Roxbury to indicate the ledges, which you can see here. In fact, I used this to find them myself, and this is now Tremont Street, and they are right beside Tremont Street. They're still there. And they would take the stone down either to the town landing, or they could take it through a convoluted path out to the full basin, or I think more likely they kept it on carts or wagons until they got to this loading point. Today's Mission Hill neighborhood backs right onto the quarries. There's also a park in the area, and the park includes signs like this one, but none of the signs explain the geology. It's a park really dedicated to pudding stone. It was originally called Pudding Stone Park until, in the typical Boston pattern, they changed the name to the Kevin W. Fitzgerald Park in honor of a local politician. But the signs could be modified. They could add signs to explain what they did here. There's also, I was disappointed, I did a little field research and went to the Pudding Stone Tavern on Tremont Street and had a couple of beers and looked around, and there was nothing in the tavern, no images, nothing to do with the quarrying. In digging the Commonwealth Avenue underpass at Mass Ave, which we saw on the previous map, in 1937, workers uncovered the cross dam, which quickly became the focal point of an article by Wilbur Davis, Boston's chief engineer and an amateur historian. The walls of the dam fit the earlier description by Howe. Last year, it looked like the city was back at it again. So I went down there, but unfortunately no part of the cross dam was visible. The area nearby on Beacon Street also showed not a single trace of the former mill dam, which sits below the surface and in fact still carries Beacon Street. When Davis was doing this project, he got really interested, and he realized that timber cribbing called a grillage sat on the flats and carried the walls. So he actually disassembled some of the grillage, took it out, reassembled it, and took a photograph of it. This is early industrial archaeology before anyone used the term. At Back Street, the top of the Charles River seawall is visible. This is Storrow Drive in the Charles River. But the top of the seawall is really very similar to the actual mill dam. And it gives you a sense of the form of the dam that's just parallel to it and a block away along Beacon Street. Most of the seawall is from the 1860s, but some dates to before 1850. Child Hassam did a painting called Charles River and Beacon Hill in 1892 that showed that same wall. And I found this drawing of the seawall from 1872. And the important thing here is it actually shows the ballast and exactly how it's stacked against the inner wall. The dimensions, again, are very similar to the actual mill dam. And what's nice about this is you can see it from Storrow Drive. So when you drive by, you can actually see the wall. This rough sketch by my co-author, Bob Gordon, is an example of how you can build a visual understanding from fragmentary reports and diary entries, even without any historic engineering drawings. And we found very few drawings. Uriah Cotting died in 1819. Rather than give the project to David Moody, who had done the original surveys and was assisting Cotting during construction, the Boston and Roxbury Mill Corporation turned to Laomi Baldwin Jr., a professional engineer whose father had built the Middlesex Canal by 1803. Baldwin was an able man facing a daunting challenge. He wrote that, quote, "I was an entire stranger to the plan, manner of working, and mode of accomplishing this magnificent scheme which the company has formed." And this is really when engineering was in its infancy, but he was perfectly willing to take on this project. One of the things that shows here are the original channels, which continued to have high currents during the construction project. The, quote, "depth and violent current through the channels at A and at B were serious problems in 1819 when Baldwin took over the project. Current became worse as dam construction narrowed the gaps. Water rushed in both directions with the ebbing and flooding tides, making it impossible to seat a timber grillage securely on the bottom. This is a new cross-section that Chuck Parrott and I produced to show how Baldwin solved the problem. He used closely spaced lines of piles, and picture this as a long line of pilings, and he could anchor that directly into the rather firm soil below the mud. And the problem was, how do you drive piles in perfect lines, particularly in a channel that has violent currents? So his reports reveal the way that he did this. He discovered that single pile drivers on scows, like this modern one, just wouldn't work. The current just turned them around and moved them out of position, and he couldn't seat the piles properly. So what he did was to take a longer pile driving boat. And Chuck drew this conjectural image of a double pile driving boat that solved the problem. And what he really does here is put two pile drivers on it, spaced exactly the width of the lines of pilings that he's going to need to draw. And he anchors this in the channel with the current coming in both directions. That's why we have it pointed at both ends. And he moves it sideways, and they drive two piles at once. He uses two crews of Irishmen to drive these piles. And we assume that the boat had treadmills because of the lack of space for gangs hauling on lines, and because we know that Baldwin used them later in dockyard construction. In fact, when he did it later, he was criticized then for using, quote, freeborn Americans, unquote, with treadmills that had a bad reputation for prison work. But the Irishmen apparently worked on this without any difficulty, and they were able to sink the two lines of piles at once. H. McIntyre's 1852 map of Boston, which is a huge map, this is one small piece of it, shows the railroads that came through the basins in the early 1830s. The junction of the 1830s railroads that connected Boston to Providence this way and to Worcester this way was right in the middle of the receiving basin, and it's where the Back Bay Station is today. And here's another map from 1852, this one by Conant and Lincoln. And I've added labels here for the users of Waterpower so that you can see what they actually did with this power. The city mills was the first mill to be developed, and they leased this mill to William Gray in 1822. His lease was for 2 mill powers. And then in the same auction of leases, his son got the ironworks site. And his son got a lease for 10 mill powers with an option for 2.5 more. But instead of taking more, he sublet 2 of his 10 to a foundry in 1826. Gray was a persistent litigator. He's also the founder of the Boston Public Garden. His complaints about backwater and inadequate power led to legal cases, scientific testing, expert testimony, on-site metering, and advances in hydraulic engineering. And there's a whole talk on each of those. Backwater was a serious problem caused by water rising in wheel pits, thus reducing the effective head or drop and impeding the rotation of vertical water wheels. Gray's iron complex included a nail factory, which was set up by David Moody. There was also an unspecified lease in 1822 to William Appleton, the brother of Nathan Appleton, who was one of the founders of Lowell. But luckily, Appleton backed out, and it was a good thing because the Boston Roxbury Mill Corporation did not have enough power to supply the 24.5 mill powers in these first 3 agreements. This rope walk here extends out into the receiving basin. It was set up in 1825 with a 1 mill power lease, and it also solved some problems for Boston in that rope walks were highly flammable. There were a lot of fires in Boston because of rope walks catching on fire, because they tarred the rope and because there was a lot of fiber that would burn. So putting it out here over the mud flats and the empty basin was actually a good move for Boston. The mill dam foundry at the bottom here was established in 1826 with 2 mill powers leased from Gray, and it made the first locomotive in New England for the Boston and Worcester Railroad in 1833. Now, Daniel Treadwell probably made his welded cannon here by leasing space with power. He also went on in 1831 to lease 2 mill powers for a hemp mill. He was the guy who really mechanized hemp production. He also developed a really impressive power printing press. But his machinery for producing hemp and rope really made him a wealthy man. He was an inventor, a water planner, an entrepreneur, and a Harvard professor. The first Harvard professor without a degree. Very smart guy. Now, you can't see the Baldwin mills, which were established in 1825 with 1 mill power. They're down off this map, so we'll see them in this image. So you can see them here. The other mills were up here. The Baldwin mills are also drawing water, in this case from a canal off the full basin, and discharging into the receiving basin. The Baldwin mills are also called mahogany mills. The mills sawed fine woods and produced veneers for furniture shops and large customers like the Chickering Piano Company. This tidal power system was an incubator of innovative technology, including development of veneer sawing, mechanization of hemp and rope manufacturing, welding of wrought iron cannon with hydraulic force. The Boston Waterpower Company also made early efforts to install turbines, later models of which might have alleviated some of the backwater problems at the mills. One of their biggest problems was the empty basin never really emptied fully. And the water would sometimes rise in the empty basin and impede the water wheels on Gravelly Point. The last lease for water power was Treadwell's in 1831. The total of 16 mill powers was about 165 gross horsepower. This is less than twice the power of the second mill at the Boston Manufacturing Company in Waltham. Power for that mill became the standard for the mill powers leased in Lowell, which were each 85 gross horsepower. Modest or not, the mill powers of the Boston Roxbury Mill Corporation were welcome in a city without any waterfalls. The system did provide relatively steady industrial power, night and day if wanted, in an era when stationary steam engines were still inefficient and when coal was expensive in Boston. The Boston and Roxbury Mill Corporation split off the water power and all its property south of the mill dam in 1832. Essentially, its stockholders turned in half their shares for equivalent ownership in the Boston Waterpower Company. The Boston Waterpower Company quickly lost an ongoing political battle to prevent the railroads from crossing the basins. A lengthy lawsuit by the company did not produce the heavy damages that they expected. And this view shows the two railroads crossing in the receiving basin on embankments and bridges that took up valuable space, promoted ice buildup in the winter, and slowed the discharge of water from the basin. They thus aggravated backwater problems and hurt the operation of the tidal-powered mills. They also reduced the cleansing effects of discharge at low tide. Private sewers sent wastes into the basin, and noxious smells got worse. This 1840 bird's eye view from across the Charles River shortens the main dam at the fall basin, but it does show the trees that are planted along the mill dam at the receiving basin. And you can see the junction of the two railroads and also the concentration of industrial development on Gravelly Point. There are relatively few images of the dams. and of the industries they supported. An 1850 bird's eye view by Bachman has part of the mill dam at the receiving basin. So I zoomed in, and his drawing is highly detailed, and you can actually see the masonry wall of the main dam running under Beacon Street. The tolls from wagons, carriages, and sleighs were more profitable than the Waterpower leases. In this circa 1860 painting by N. Vautrin, looking east at the mill dam, no filling sluices are visible. They should be right about in here. But you can see some of these buttresses, which don't appear in any other views. The exterior buttresses that they applied where there was some swelling. And you can see the dense development at the junction of the cross dam and the main dam. And this became a pretty popular place. They had a tavern out there. There was a bathhouse. People would sleigh ride out there in the winter. The 1858 panorama that you see here is really two joined photographs from the State House, and it looks west along the main dam with the cross dam and some of the mills visible. They've just taken out the rope walk, but parts of the facility are still there, and this is the ironworks here. You can see the buildup of sediments that created problems in the receiving basin. Public health concerns played a role in turning the foul-smelling Back Bay into a giant real estate development. But the biggest reason for the closing of the tidal power system and the filling of the Back Bay was the growth of the city and the rising value of land near its core. The filling began in earnest in 1858 and continued into the 1890s. Dioramas of the Back Bay are tucked away in an office building lobby. They show only the pre-industrial past and the filling process, not the era of unique perpetual tidal power and innovative manufacturing. Few visitors enter the former New England building to see this diorama, which was created by the Museum of Natural History after 1863. And this is kind of a wild exaggeration of Beacon Hill, for those of you who know Boston. Groundwater experts Harl Aldrich and James Lambrix drew this section showing pilings, strata, and the lowered water table in 1986. The mill dam, which is breached in a few places, is still under Beacon Street. Filled sluiceways are also buried there. The structure is relatively impervious to flow across its long axis, and therefore acts with other barriers in limiting recharge of groundwater in the Back Bay by the Charles River, which has been dammed since 1910. This, combined with water loss leaking into things like sewers, subways, highways, and construction excavations, has caused water levels to sometimes fall below the tops of the wooden piles. So you can see the groundwater table falling below the tops of the piles, and that is devastating to wooden pilings. And most of the buildings that have historic character in the Back Bay are seated on wooden piles. And there's been a resulting decay and expensive remediation required. And this damage has created a preservation crisis. And now they're making a lot of efforts to keep the level high enough. The heavy gravel fill has also compressed some of the organic silt and peat, and that produces negative friction on pilings and actually pulls them down underneath the buildings. So there's been quite a problem with a number of the major buildings. We still deal with both the positive and negative legacies of an overlooked tidal power system. You can learn a great deal about the changing form of Boston from this map and Alex Krieger and David Cobb's Mapping Boston. And you can see the original peninsula, and you also can see the Back Bay and the incremental filling, and then the massive filling project that began in 1858. You also can see how Boston has expanded in various directions over time. Walter Muir Whitehill, a noted scholar, said that the mill dam in the Back Bay, quote, was to change the shape of Boston more completely than any other single undertaking in its history. Yet almost no one walking down Beacon Street in the Back Bay realizes that they're on top of a 1.5-mile tidal power dam that was responsible for the city's largest land-making project. We need to create awareness of the industrial heritage of the Back Bay and learn more from its underground features. Extensive signage and guided or self-guided tours are among the interpretive possibilities. And whenever construction or infrastructure projects threaten to impact historic features beneath the streets, industrial archaeologists must be there to record and protect precious traces of a forgotten perpetual power system. Thank you.
So we have a few minutes for questions.
So I was interested in one of the earlier images you showed where Fenway Park is, right, in relationship to these. So how did that end up in this particular place? Was it tidal when it was built? Was it already in the dam?
It's probably right at the outer margins of the full basin and in the marshes that led over to Brookline. And the work that resulted in how actually documenting the dam took place at the fin, because they had to have an opening for the rivers once they filled the basin. And as he dug through the mill dam, he was able to actually discover exactly how it was built. Fenway Park is obviously, when you say Fenway Park, now everybody thinks you mean a baseball field instead of the Fens Park, which is really the proper name for homesteads.
My question is, how much do you think that mill culture in the greater Boston area contributed to the economic decline?
I'm a little hard of hearing. Could you?
I'm sorry. Oh, so how much do you think that the mill culture that we're speaking about today contributed to the economic decline that we see currently in the Boston area?
I think it was quite important, particularly because of the innovations. For instance, the rope-making machinery was bought in large numbers by the Navy, in particular in Charlestown at the Boston Naval Shipyard. The veneer operations were continued, and even after this operation closed down, the technology of veneer sewing really became important in Boston furniture making. Chickering Piano located their spectacular factory, one of the biggest buildings in the United States, right near that Mahogany Mills complex. But then the Chickering Company really pulled a surprise on the Baldwin Mills and established their own veneer operation in their new factory. So a number of these mills ran successfully up until the 1850s. The total amount of manufacturing is small. We can't deny there's really not that much power. It was not financially profitable. It didn't make a lot of money for Boston. In fact, it ate a lot of money that might have gone for other things. But this was an era when steam power was not yet fully perfected. And by 1849, when George Corliss from Providence develops a highly efficient steam engine, that's right at the end of this era, and just as they start closing down. So you could switch to steam power, and Boston did. But I think the manufacturing traditions were still very important.
So thank you for a great talk. But forgive me, I want you to tell these people about something else you did. Tell this audience, please, a little bit about James Francis and how this is from Pat's book, Waterpower and Lowell. Francis needed to produce an awful lot of water power in Lowell, and within 20 years, he was using the entire watershed of New England to accomplish that. So New England, the entirety of New England became a site for industrial power. And it's a complicated story, but a fascinating one. So if you would tell people in brief how Francis pulled that off over many, many states.
Well, Francis is, of course, really one of the great engineers of the 19th century. And as you know, I've written quite a bit on Lowell and his work. There was so much capital, so much profit being made in Lowell and in Lawrence, which was established around 1845-46, that they were able to develop a huge watershed and to buy up the water rights to lakes in northern New Hampshire. So they ended up with 5 major lakes in New Hampshire, all feeding the Merrimack. They even ran telegraph lines up there, and they could time when they needed water. If they needed extra water, they'd send a telegraphic message and they'd open the gates. But they suffered from backwater almost half the time in a given year. And that's because the river would flood. They couldn't really stop the river from rising. And if the river rose, then mills that were discharging directly into the river suffered from backwater. And that's one reason that Francis went into turbine development, because turbines behave so much better in backwater than breast wheels do. So Francis, goes into a development program that resulted in highly efficient turbines that provided the power for these mills that could then use this huge flow of water from northern New Hampshire, over 100 square miles of drainage space. He buys that up. I was interested in doing this project that Francis appears in this. And what happens here is this Horace Gray, who sues everybody, is a really obnoxious customer, but he's somehow connected with some of the people in Lowell and enemies of others. And Francis doesn't want to be involved in this at all because there's no winners in this. So Horace Gray asks Francis what he thinks about the backwater problems in the Back Bay. And Francis says, nobody knows anything about backwater. Nobody understands it. The court case, the commission, I really depended heavily on legal cases to look at this. And Francis says, well, I don't really want to testify, but, I'll give you some advice. And so Francis stays out of this. But as soon as the court case is settled, Francis starts testing breast wheels in backwater. And the only test ever done with breast wheels in backwater. It was never published because turbines took over by the time he was ready to publish that study. But we have the actual journals. So we have all the studies that he did of breast wheels and backwater. And we can compare those with the much cruder tests that were done as part of the legal case in Boston. But I think it's fair to say that the Back Bay litigation resulted in greater advances in hydraulic engineering than anything else in that era. They really caused everyone to think about water power and hydraulic engineering, and they got Francis interested in figuring out how to test water wheels and then test turbines.
Would you mind talking a little bit about the T and the green line that goes through Back Bay and how those two things might be connected?
Okay, the rail lines are still pretty much where they were. So if you're going T-rail, either from Worcester or from Providence, you're basically following that route. It diverges at the end because South Station's in a different location than the previous Boston and Worcester station. The T that we think of, like the orange line, for instance, is really a totally different line, and that was not part of this system. And one of the things that's nice about the orange line is that was a failed highway plan that Governor Sargent vetoed. They were going to drive a superhighway, and they did level everything on the way into Boston. And after Sargent canceled that, they changed and used it for a park and put the Orange Line right underneath it. So that works very well for Boston. Nice to have somebody here that knows the landscape.
This is actually less a question than a comment, which is that I really see in this, like you've talked about how we could have much better signage, ways of marking and telling us what's going on underneath. But I'm also thinking that there's opportunities for landscape architects and urban designers to be able to, in some way, interpret and bring that in, right? So something beyond signage. But I think for any landscape architect or urban designer working in Boston, it would be really great if they learned about this history and what's going on underneath as something that they can then work with, better understand. Like, from this, we understand, okay, here's why we have these particular structural problems with pilings, right? Otherwise, we don't really, you kind of, here's a place with the problem, and here's a place with the problem. But if you actually understand, okay, here's this big structural problem, are there bigger systemic ways to think about how might we be able to bring water back in there by understanding what's there, right? So I feel like there's opportunities for design more broadly to engage this too.
I think you're absolutely right. And certainly the Boston Groundwater Trust has been paying a lot of attention to the historic structure now, because they do realize that this affects the recharge, and they need to understand it. I, for instance, they had no idea how many sluice gates are out there. I showed you there's 6 in the full basin and 5 in the empty basin. They didn't know what they were doing when they started doing this. They estimated they were going to need 30 for the empty basin. And when Baldwin took over, he cut it to 16, and they didn't work. So he built 5 deeper ones, and the 5 deeper ones did the job. But all of those 16 are still out there somewhere, filled in. You kind of wonder. I mean, there's all sorts of things. The difficulty for landscape architects, and I've worked with a number of them on interpretive projects, is, it's one thing to just put a mark on the ground that shows, for instance, that image that I showed of the millstone. There's also a sidewalk mark that shows where the edge of the old mill pond was. But I don't think anybody knows what that is. I mean, I once excavated a whole square in Woonsocket, and they went out and put like blue lines on the parking lot. There was no explanation of what they were, but there was the whole industrial complex kind of outlined in blue lines. I never thought it worked. But there are creative ways to do it that might be a lot more informative. And combining features with signage and with tours. I'm all in favor of people walking people around and explaining it.
Hi, thanks for a really interesting talk. So I'm not an architect or a landscape designer or anything, so maybe this question is very naive or something. But having lived in Boston for a while, like it seems like the geography that this map shows, right, has been like especially obliterated compared to other cities. Yeah. Like you'll drive along Mystic River Parkway, and the one thing that you can never see from Mystic River Parkway is like where the river is or any, or what's going on. And so is there something like about the history of Boston or the political culture of Massachusetts or the particular thread of economic development in that region that has like led to this I don't know, it seems to me like a complete erasure of that, of the actual landscape?
That's a good question. I mean, a difficult one. And obviously, we would all have our own biases about that. But Boston seems to have had an obsession with expansion from a very early era. And Nancy Seychell's book, Gaining Ground, is really good on this. She doesn't really get into the philosophies behind it, which I think would be quite interesting. But whenever Boston has needed any land, they didn't hesitate to just fill in something. And they did it with impunity. They also, of course, fill with the hills. So if you look at the history of Boston, you find that they take down Beacon Hill and they start to fill places around their peninsula. And they're constantly changing the landscape, changing the contours of the topography. And their approach to the sea has also been very interesting, because now environmental historians have begun to look at the whole issue of tidal flows in and out, and how the changes in the Charles River. For instance, a lot of people don't realize that the Charles River was tidal, as we know from this talk, but in 1910 they put a dam across the Charles River, and they established an artificial level. So when you go out with your kayak, you have to go into a lock and actually change elevation. It's a completely different landscape. And Olmsted designed the fens for a tidal landscape. So he designed it with plants that could deal with brackish water. And they had to change the entire planning system in 1910 when they turned it into a controlled pond for the Charles River with nothing but fresh water.